Alrighty, welcome back. In this video we're going to review problem number 3 on assignment number 1. This problem is probably one of the more complicated problems on the assignment. It gives us fixed cost associated with this production cycle, variable cost of $20 per unit, and then a quantity to price equation. And we're asked to find the break-even point, the maximum possible revenue, the profit at the maximum possible revenue, and then the maximum possible profit. So in solving this equation, we need to develop a cost equation. And keep in mind that the cost is nothing more than the variable cost plus the fixed cost. So in this case, we have a variable cost of 20 times the number of units produced plus the fixed cost of 10,875. In addition to this, we're able to determine a price equation by algebraically manipulating our quantity equation so that price is equal to $250 minus 1/4 of Q. This is nothing more than just throwing a little bit of algebra at this in order to arrange it so that we have solved for P instead of Q. In addition to this, and this is probably where this problem is particularly challenging, the revenue is defined as the price times the quantity. In this case, we know that the price is defined from this equation, the quantity is the dependent variable or independent variable. Therefore, what we see is that when we take price times quantity, we end up with 250 times the quantity minus 1/4 of the quantity squared. So if you look at the graph up here in the center of the board, we have the cost equation modeled right here, and as you can see, just as you'd expect, it is a line. The revenue equation then is the blue graph. It is a parabola, and in fact when we go through we'll see that because of our parabolic revenue function we have 2 break-even points rather than just 1. So in order to determine the break-even point, what we're going to do is say that that break-even point occurs when the revenue is equal to the cost. So we're going to go through and say that we have 250Q minus 1/4 Q squared. This graph equal to 20Q plus 10,875. All I'm doing is looking for those 2 points where the 2 graphs intersect. When I go through and plug this into a polynomial solver, some kind of quadratic solver such as on your calculator, we find that the 2 break-even points for this particular problem are 50 and 870. That means that we're going to be breaking even as long as we produce at least when we're producing exactly 50 units and when we're producing exactly 870 units. If we're producing less than 50 or more than 870, we're losing money. We have to produce within that range in order to be profitable. Our next part of the problem is to determine the maximum possible revenue. And in order to do this, what we do is, or one approach to this is to use a little bit of calculus. We can treat this as a maximization problem if we like, and say that the derivative of the revenue equation with respect to the quantity produced is equal to 0. What this is looking for is the point on the graph where there's no slope. For those of you that have not had calculus yet, there's an alternate way, and this is probably a little bit more straightforward. We can say that because the revenue is quadratic in nature, it is going to be symmetric about the vertex. So the stuff on the left-hand side of that vertex is going to be a mirror image of the stuff to the right of that vertex. That means that if we know 2 points on that graph that are at the same elevation, say this zero crossing and this zero crossing, we can find the location of that vertex just by averaging them. And for that reason, what I did was I said, okay, well, we know our 2 zeros for the function. They're at 0 and 1,000. We add those 2 values together, divide by 2 to get the average. We see that the maximum revenue occurs at 500 units. To determine the revenue then, we simply plug in 500 units into our revenue equation. 250 times 500 minus 1/4 of 500 squared, and we get the revenue, or the maximum revenue of $62,500. Next part of the problem is to find the profit at maximum possible revenue, and we know that the profit is equal to the revenue minus costs. So in this case, since we've already calculated the revenue at 500 units, we only need to calculate the cost at 500 units, take the difference, and when we do so, we find that the profit at the maximum possible revenue is $41,625. Finally, in order to determine the maximum possible profit, we're going to develop a very similar process as we did for the second part of this problem. We're going to recognize that this right here is essentially our profit equation. Now there's some slight problem with the signs here. That doesn't hurt us at all for this particular equation, but what we see is that when we apply it to our profit equation, it does change the sign slightly. But the process is the same. So essentially what we do is, since we know that these 2 points are equidistant from that vertex, in order to find out where the maximum revenue is, we're just going to average those 2 values and find that the maximum profit is going to occur at 460 units. We then take that and plug it into our profit equation, and when we do so, we find that the maximum possible profit is $42,025. This is pretty important to us because it makes us very aware of the fact that the maximum profit does not necessarily occur at the same point as the maximum revenue. And you got to keep that in mind as we're going forward. So hopefully this helps answer questions on problem number 3. We will next take a look at problem number 4.